This is a video that is going to go over the questions that were most missed on exam number 2 in the fall of 2023. The first two questions are questions 5 and 11. These two questions happen to have the exact same choices on both A and B, but in a different order. And what I've shown here are questions from the test version A. So let's start with question 5. Which of the following statements about partial charge is correct? So let's first just review what partial charge is. If we have a bond between two atoms, X and Y, and let's imagine that this bond is polar, and let's say Y is more electronegative than X. That means that these shared electrons are going to be pulled in the direction of Y, and that's going to make Y partially negative and X partially positive. And that's because electrons are negatively charged, and if they spend more time over here, Y is going to get a little more negative. That's going to leave X deficient in negative charge, so it's going to be partially positive. So let's look at each choice and determine why it is that B is the correct one. So let's go. We're going to go through all the wrong choices first and then come back to B. The nitrogen-chlorine bond in NCl3, which is shown here, has no partial charges. First of all, let's just evaluate that part of it. Is it true that the NCl bond has no partial charges? Well, if you look at the electronegativities of nitrogen and chlorine, they have the same electronegativity, which means that there is no bond dipole like this. So that means that there are no partial charges. So this part is correct. But the question is the explanation correct? Is it because the lone pair electrons on the chlorine balance out the bonding electrons? Well, we've just learned that the reason you get partial charge is because the electrons that are shared unequally. There's nothing to do with these lone pair electrons somehow balancing out the bonding electrons. So that doesn't make any sense as an explanation. So we can eliminate choice A. Let's go to C. In FCl, which we've got here, the F is partially negative because it is small and has a lot of valence electrons. Well, first of all, let's ask about the first part of it. If fluorine is bound to chlorine, is fluorine partially negative? Well, you probably know that fluorine is more electronegative than everything else, so whenever it bonds, it's generally going to be partially negative. That's going to leave the chlorine partially positive. So this part is true. It is partially negative. But the question is it because it's small and has a lot of valence electrons? Well, it might have to do with that it's small. That might contribute to the electronegativity, but largely it has to do with underlying this in that fluorine is a core charge of +7 in a very small atom, as opposed to +7 in a larger atom. So it doesn't really have to do with there being a lot of valence electrons. So we're going to eliminate choice C. All right, the next one is also about fluorine and chlorine. When they're in a covalent bond, there are no partial charges because they both have a core charge of 7. It is true that they both have a core charge of 7, but they have differences in electronegativity. Different electronegativity. So, and the reason they have different electronegativity is because while they both have a core charge of +7, fluorine is much smaller, and so the electrons are going to be more stable and want to get closer to the fluorine. So it is not the case that there's no partial charges, so we can eliminate choice D. Any other atom covalently bound to a fluorine atom will have a partially negative charge because fluorine is the most electronegative atom. It is true that fluorine is the most electronegative atom, but that makes fluorine partially negative because it is so electronegative. All right, So we've eliminated all the choices but B, but let's make sure we understand why B is the correct answer. In a carbon-hydrogen bond, which we classify as nonpolar, its electronegativity difference is 0.4, but we said that's right on the borderline, and we're going to call that particular bond nonpolar. So that part is true. The partial charges on carbon and hydrogen are very small, and that is true. If we were to draw the electronegativity difference with a bond dipole, we would see that carbon is a little more electronegative than hydrogen, but not a lot, right? That's why it's got a small electronegativity difference. But it's not a zero difference. And that means one way to think about this might be that we draw carbon, hydrogen, and we say there's a little itty bitty dipole, right? Like not a big one. So let's get rid of this one that looks kind of big. Little bitty dipole, and when you have a little bitty dipole, that means that you're going to have a little bitty positive and a little bitty negative. So the partial charges on carbon and hydrogen are going to be very small. All right, so for this next one, this one was tricky, but you can solve it by drawing shell diagrams and core diagrams as needed. So this is the question says, consider the size of these atoms and ions, and it happens in this case that they're all ions. Which is a correct ordering? So we're going to go from bigger to smaller. I'm just going to focus on the correct answer here. And I'm going to pause my video. I'm going to draw a bunch of shell diagrams, and then we'll talk about why it makes sense that they're in this order. So I'm going to start with sulfide, chloride, and calcium. One thing you can see from the shell diagrams that I've drawn is that these are isoelectronic. So they all have 18 electrons. They're isoelectronic with argon. But they're not all exactly the same because the core charge experienced by the sulfide is going to be +6. For the chloride, it's going to be +7, and for the calcium, it's going to be +10. Let's make sure we know how that gets calculated. Remember that the core charge is the full nuclear charge minus the charge of the shielding electrons. And so in the case of sulfide, you would take the 16 protons, add the charge from the shielding electrons, which is 10, and you end up with a core charge of +6. So you do that same thing for each of the others. Notice that in this case also, that all of these have an n = 3 valence shell. Calcium normally is in the n = 4, but it's lost 2 electrons. And so now its valence electrons are in the n = 3. So if we were just to compare the size of these three, what we would say is they all have the same number of electrons, or isoelectronic. They all have the same number of shells. So the thing that's going to make a difference is what is the size of the core charge. The larger the core charge, the smaller the atom is going to be. So this is going to be, of these three, this will be the smallest, and this will be the largest. That doesn't mean it's large, it just means it's larger than the other two. So let's just notice that in any other choice where these three aren't in that order, you could eliminate it. In this particular case, notice that I have these three right in the center in that order. Now, we have to convince ourselves that the rest of the order is right, that selenide and beryllium 2+ would be on the other side of these examples. So beryllium 2+ is going to look like this. It's got 4 protons. It has lost its 2 original valence electrons, and now it's got 2 electrons. It is isoelectronic with helium. And while it does have a smaller core charge than these others, it only has one shell, so there's no way that it can be bigger than any of these. So beryllium is going to be at this end. Selenide is in the same group as sulfide. So its core charge is also going to be +6, but it's got another shell. So it's going to also be larger than sulfide is. So we get selenide is biggest, then sulfide, then chloride, then calcium, then beryllium. Okay, so this, the next question I want to go over is question 13, was about which is the invalid Lewis structure. And this one really threw a lot of people for a loop. These are the incorrect answers on each of the exams. And I'm going to go through why they were incorrect, and then we'll go through, meaning they were the correct answer because I was asking for an invalid Lewis structure. And then we'll talk about this one because this is the one that really threw people off. So let's start with NO+. What I'm going to do is first note that nitrogen would bring 5 electrons, oxygen would bring 6 electrons, and this structure has a plus, so it's going to be minus 1 electron. So that's going to give us a total of 10 electrons in that structure. And let's look, it's got 2, 4, 6, 8, 10, 12. So this is not a valid Lewis structure because NO+ should only have 10 electrons. Let's do the same thing with the next one. We've got chlorine, Chlorine would normally bring 7 electrons. Oxygen would normally bring 6 electrons, and we've got an extra, let's spell extra correctly. An extra electron, so we should have 14 electrons in this structure. And so let's look, and we've got 2, 4, 6, 8, 10, 12. So this one has too many electrons, this one has too few electrons. In either case, the invalid structure is either this one or this one. Now let's go back and look at this answer because this is one that gave a lot of people problems. And I had a number of people ask about what does this plus mean? And maybe I should have told the whole class, but I figured if people were confused, they would ask. This is equivalent to saying this. HOH with the 2 lone pairs with a plus. So this just means that this is a structure that overall has a plus. And I'm sorry if the lack of brackets confused you, but let's make sure that we believe that this is correct. So normally you would have 3 hydrogens would bring 3 electrons. We've got 1 oxygen that brings 6 electrons. And we have a plus sign, so we're going to do minus an electron. And so that's going to give us 8 electrons. So let's count. 2, 4, 6, 8. So that's good. We've got the right number of electrons. And then we have to double check that everything has an octet. So I see the hydrogens all only need 2, so they're fine. Here's this oxygen, has 2, 4, 6, 8. So it has an octet. Check. So this is a valid Lewis structure. So in question 16, I was giving you a different periodic table to make sure that I could probe to see, do you understand how the periodic table reflects electron configuration? So in the problem, I told you that the green sections are the S block, the yellow sections are the D block, and the blue sections are the P block. So in that respect, it looks a little bit like our own periodic table. And let's just imagine I had asked you to do this atom. What is the electron configuration? So what I was hoping you would see is that this is the n equals 1 shell, this is the n equals 2 shell, and this is the n equals 3 shell in analogy to our own periodic table. Now, the green are S's, so that would mean that there must be 1, 2, 3, 4 1s electrons. So we would do 1s4 to cover 1, 2, 3, 4 positions in the periodic table. Then we'd have to go down to the n equal 2 shell, and we would start here with the S's. Again, there would be 4. 1, 2, 3, 4, that's what we're accounting for, 2s4. And now we're going to go into the p block. And notice that there's 1, 2, 3, 4, 5, 6, 7, 8 p's, 8p electrons. So we'd be 2p8. And it's still 2 because we're in the n equal 2 row. And that means we've ticked off these positions in the periodic table. The next atomic number starts here at 17. So we're going to need to go to 3. And again, we're in the S. Again, there's 4 electrons. 1, 2, 3, 4. Now, what's clear is that what comes next is a D block. And some people asked, is it like ours? Does it fall back by 1? And I was assuming that, but I took it whether you did 2D or some people did 3D, and I took either one. But notice in this particular D block, there's 1, 2, 3, 4, 5, 6 electrons. So 2d6. And then we would move into the 3p, and in this case, we just need 2p electrons. So that would be what I would get for if my atomic number was 28, which was not exam A or B, but you can see how it got done. Now, some people were able to do this, but got messed up by the next question, which is how many orbitals do you think are in the S subshell or P subshell in the alternate universe? So let's take the S first. What we can see is the S fits 4 electrons. And in the problem, I told you that orbitals hold the same number of electrons. So orbitals hold 2 electrons. And so if the S subshell fits 4, then we must have 2 orbitals in the S subshell. We can do the same analysis for P. P here fits 1, 2, 3, 4, 5, 6, 7, 8. And if each orbital holds 2 electrons, that must mean there are 4 orbitals in the P subshell. This is hard because you really have to have your head wrapped around what does it mean for the periodic table to be laid out the way it is. And that will come as you get better at it. Okay, I'm not going to go through this whole problem because you can read the key once it's posted, but I want to just talk about the elements of a really good answer and talk about a couple of things that I saw that were common errors. So what this question asks for is first define ionization energy. So not everybody did that. And in some cases, people added things or confused ionization energy with electronegativity or something else. But ionization energy is the energy that it takes to remove, the easiest to remove electron. One electron, not multiple electrons, not all the valence electrons, just the easiest to remove electron. And if you weren't precise in that answer, you might have lost something on that part of it. The second part is summarize the factors that govern the stability of an electron and how they work. So sometimes people mentioned the factors but didn't actually say how they worked. So the three factors I was looking for was core charge, the number of shells. I also accepted distance here, and electron repulsion. Now what I was looking for in the how they work is I was looking for larger core charge makes an electron more stable and requires more ionization energy to pull off. For the number of shells, what I was looking for is increased number of shells or increased distance makes the electron less stable and therefore requires less ionization energy. Most people got those two or one of them very clearly. This is the one that people often left off entirely, electron-electron repulsion. And what I was looking for here is the more electrons in the valence shell, the less stable the electrons and the easier it is to pull off. So that means less ionization energy, all other things being equal. Now, this is one where sometimes people talked about electron-electron repulsion, but actually made the opposite argument. Basically made the argument that the more electrons, the more stable. And that is actually not true. Electrons are negatively charged and they don't want to be near one another. They are going to repel each other. And so if they're packed all in together, that is destabilizing. And so that means it takes less energy to pull it off. This is a very common misconception because people somehow think, oh, noble gases are stable. They have lots of electrons. That must mean that lots of electrons make it stable. But it is not the case that the bunch of electrons is what makes it stable. What makes it stable is the interaction with the core charge and something called orbital angular momentum that comes from having a full shell. Okay, so if this is confusing to you, come and talk to me about it because it's not trivial to get your head wrapped around it. So the last part that I was looking for explained why for each of these steps, from helium to lithium, neon to sodium, and argon to calcium, why there's such a big drop-off. So what I really wanted was, what are the specific ways that each of these varied? You didn't have to do all of them, you could pick one of them, but you needed to explain to me what happens with core charge when you make a change, for example, from helium to lithium or neon to sodium, and how does that help to explain this or this or this, and what happens to the number of shells when you're doing this or this or this, and does that help you to explain that the ionization energy goes down, and what's the deal with electron repulsion? Even if you think electron repulsion wasn't important in this case, what would electron repulsion predict for these variations? So what I'm trying to do here is make sure that I give you an opportunity to really spell out the nuances of what you have understood. There were some problems, some answers that clearly you had some grasp of some of the pieces, but you hadn't practiced explaining it and using the language enough. And I can't emphasize enough, using the time in class to talk out loud and to write things down is how you get better at these kinds of problems. All right, better and better every time.